lambda y, and this is what we were talking about a second ago. Let's move everything over to one side. Factor out a y. And you get two possible answers here. Y is 0 or lambda is 1, right? Okay, can y be 0? Well, let me clean up this. Let's clean this one up. Y equals 2 mu z, right? We have that. And then this one doesn't really clean up, does it? Not really. Let's just leave it. Okay. So let's say that y is 0. Let's just say y is 0. If y is 0, then you see that means that would be 0. That means mu would have to be 0 or z would have to be 0. You have to look at those two cases. What about if y is 0 here? You get this equation, right? You have to work with that. So you see you're going to have to go down like different roads here. One road is let y be 0, see what happens. And then when you're doing that, you might have to look at two different cases. And then you let lambda be 1, and that's a different case, and you see what happens. Was there a question?
Yeah. Huh? Could you just quickly look at equation 4 in this case and be like, okay, that's not possible?
With what?
If y is 0?
Yeah, so we would have gotten to that. You noticed it right away. If y is 0, what happens? Equation 4 can't be true. Right. So you can throw that one out, right? So you can just throw this away. That's not possible. That means lambda has to be 1. Has to. And if lambda is 1, look what happens here. If lambda is 1, do you see that these x's on both sides go away? So you get z is equal to 2 mu y. And then you have another equation with z. You can set them equal to each other. You can start playing with the other equations. There's a lot of things you can do. Yeah? Now, when I first put my notes together in this class, which was years and years ago, I said, you know, this is all great, but really at the end of the day, it's just solving equations, right? Nonlinear equations. So why not just write some code to solve the equations for me, right? So I went ahead and I created these calculators at the end of our notes where if you have a function of 2 variables with 1 constraint, you can put the things in here, it'll calculate it. If you have a function of 3 variables with 1 constraint, you can put your stuff in here, it'll calculate it. If you have a function of 3 variables with 2 constraints, that's the problem we're doing right now. It'll calculate it. So the way it works is, I already did this right before class. Here's our function, right? It was xy plus yz. And then the first constraint was that x times y must equal 1. And then the second constraint was that y squared plus z squared must equal, why is it not showing up here? Why is that not showing up? Oh, there it is. Okay. Is 4. Was it 4 or 1? It must have been, yeah, this problem was 4 or 1? It was 1. Oh, I accidentally put 4. Well, I'll do it again then. Make it 1. 1. There we go. And then what you do once you type them in is you hit this little U up here, and it updates everything. There you go. And it gives you the answers. It tells you what x, y, z, lambda, and I put m for mu. Okay? It tells you the values of all of them. And we have, and then this is actually the value of the function f at those. So you can see we have maxes at 2 different places, right? And we have min at 2 different places. But the maximum value is 1.5, the minimum is 0.5. So you can see how you'd use a computer in the real world for something like this. Let's look at the code. I haven't seen the code in a long time. How complicated is it? I don't think it's that bad. Let's see. What do you think? Pretty short. Yeah. It's not that bad. This is really like the brains of what's going on in the code is right here. This is all just format stuff. So I'm using a lot of built-in functions in Mathematica to do this. I'm having it differentiate for me. I'm having it solve for me. So this isn't true like C++ or something like that. All right, we happy? Not happy. Are we done? You okay? Move out of Lagrange? Yeah? Okay, let's start chapter 12. Chapter 12, yeah? Chapter 12. Chapter 12, let's do it. So chapter 12, we start doing integration, okay? Multiple integrals. It's not as bad as it sounds. It really isn't. I think you're going to appreciate what we're doing here. I think you might actually like it. Where is it? 12.1, the double integral, or double integrals. All right, so to do this, I want to take you back to Cal 2, all right, and what just a regular integral was. And depending on your professor, I don't know how much they stressed to you what the notation of the integral actually meant. So I want to really make sure that you understand what's going on here. So back in Cal 2, the whole idea was that we were trying to find an area under a curve, right? And the way that we did it is we approximated the area with a bunch of rectangles, all right? And then what you had to do was sum these rectangles up, right? Add up all the areas of these rectangles. And then what you would do is you would just get more rectangles, right? You just add more and more rectangles in there, and the more rectangles you have, the better your approximation becomes. And if you could somehow let the number of rectangles go to infinity, then that gives you the true area, right? But ultimately, what we did to set that all up is we said, okay, look, if I want to know this area, what I'm going to do is slice it into a bunch of little rectangles. And that rectangle right there, if I wanted to know the area of that one, right? If I want to know the area, let's call this the kth rectangle, okay? If I want to know the area of that kth rectangle, what it's going to be approximately is the height of this function, right? How tall it is, right? The height of that rectangle is the function evaluated at some point in here, right? I'll call that x sub k. It's just some x value in that rectangle, x sub k. That's about how tall it is right there, right? And then how wide is it? Well, we normally put delta x, which would be the change in x. And the change in x for all of these is the same because we're cutting them into equal rectangles, equal width. So this is just dx, delta x, delta x, delta x. So the area of that one is the height times the width, right? This is your height times the width of the rectangle. And then we need to add that, right? We need to take that and we need to add to it all the others, right? So then we throw a summation in here. We say, oh, we need to add up all of these guys, right? And we need to let k go from our first rectangle to our last rectangle, which we just say n. We have n rectangles. That would give us the area of the n rectangles. And then what we do is we say we want to take the limit of this as n goes to infinity, right? And that right there is where the integral sign comes from. The integral sign from a to b, right? So let's say this left endpoint's a, this right endpoint's b. The integral from a to b of f of x dx is the way we represent this idea, all right? So when you look at this right now in this class, the way that you should see it is you're adding up an infinite number of things, right? What are those things? Well, it's the function evaluated at some value x. It's the height of the function, right? Times the dx was like the delta x times some infinitesimal width. So these are a bunch of areas, right? A bunch of areas. Height times width, height times width. Yes? Okay, that's at the heart of what that integral sign represents. So now let's talk about double integrals, right? What's a double integral? Well, the goal is similar to what we had in Cal 2. We wanted to know the area under a curve, right? Well, what have we been working with here? Functions of not one variable, but two, right? Functions of two variables, which look like what? What's a function of two variables look like? If I give you z as some function of two variables, what does that look like in three-dimensional space? Could be a plane, just a surface, right? Just some surface. So let's say that we take some surface floating here in three-dimensional space, right? Now, of course, this thing goes, floats around here. This is This is our function f, right? What do you think I want to know about it? I mean, instead of like a curve finding the area below it, what do you think I could try to do here? Find the volume underneath it, right? But I would, just like in Cal 2, if I had a curve, I would have to what? Start at A and end at B, and then I could find the area here. I'm going to have to do something similar here, aren't I? I'm going to have, if this surface is floating around, I'm going to have to restrict it. And so when we restrict it, we're restricting it to something on the ground, the domain, right? So how do we want to restrict this surface? Remember, this surface, let's just say, goes in every direction. So I need to restrict the domain on the ground. What do you think the most simple domain restriction is possible? That's pardon? Well, I mean, what shape is it, do you think? What's the most simple shape on the ground that you could have for a domain restriction? Square, or how about a rectangle? Yeah? Like I could say, all right, only take values. Let's see if this makes sense. If I restrict, this is x, this is y, okay? If I say my x goes between a and b, right? That's from here to here. And then my y goes from, let's say, C to, let's say, D, C to D, then I'm going to have something that looks something like that. Do y'all see that on the ground? And so what I'm saying is that if you were to project this domain up into the function, right, it would create some shape up here, right? I don't know exactly what it, let me change my picture up there. Let me change this a little, make it a little bit bigger. Let's make it like this. Okay. Now if I restrict and only plug in values in this little domain up into this, I'm going to get some shape up here, like maybe it'll look like this. It doesn't have to be straight lines here, does it? Wavy, okay? Like that. Do y'all see that? Now, drop down like this. And do y'all see that solid kind of blocky object I just created? What's the volume of that? Right? That's the question. It's this question, but now with a surface over some domain. That's the idea of a double integral, right? That's the idea of a double integral. So, all right, I have better animations here. I just wanted to draw it for you before I put it, just slap it up on the board. So we would like to know the volume of this, right? Well, what do we do over there? We cut it into a bunch of rectangles, right? And then we found a formula for that. We found the formula for the area of one of the rectangles. Then we added them up with this summation. Then we took a limit and let the number of them go to infinity, and that created the integral, right? So we can do the exact same thing here. Except, is a rectangle going to work? Probably not, right? Rectangles are flat, two-dimensional. So this is just me saying where all that stuff came from, okay? So now let's look at this. So that's my picture again. Okay, that's my picture again that I just gave you. We were trying to find the volume underneath that shape. Well, if we want to find the true volume of this thing, can't we just cut it into a bunch of blocks? Just a bunch of blocks. And we can find the volume of each block, and then we could add them up, right? Add them up. So here's where things get really, I guess we have to be really pay close attention to things. There's the picture. I hope that this all makes sense to you. Here's the domain that I just showed you on the ground. This is us looking from the top. We go from A to B, right? From C to D. We have all these blocks that are going to come up out of here, right? Oh, I should have scrolled back real quick. Let's scroll back. Of course, we want more blocks, right? The more blocks we put in there, the better and better and better and better it gets, right? As far as an approximation. And if we could let the number of those blocks go to infinity, we should get the true volume, right? So same exact concept as in Cal 2. So we start off with just, can we find a formula for the volume of one of those blocks, right? Just one. So I go in here. Now, right now I've only cut it into 9 blocks. Do y'all see that? But imagine there could be, a million of these. But let's look at just one. This right here is delta x, just like it was in Cal 2. It's how wide the x is. But now I have another delta. This delta y is how long the block is, or sorry, this kind of depth of the block, right? So that's this picture over here. This is yellow. That over here, delta x, delta y. Here's our A to B. Here's our C to D, right? Now, how tall is the block? Well, it's the height of the function, isn't it? At some point in there, right? So there's some point in here that if I plug that point in, it'll hit that surface up here somewhere, and that's how tall it is. It's that right there. So what's the volume of that block, just that single block? The volume will be approximately the height of the function there times the width times the depth, right? Volume is length times width times height for a block. So we get that, right? All right. Well, then I would want to take a sum, wouldn't I? I would want to sum, and the way I sum, I want to kind of make this clear. Go with this picture right here. Let me back it up a little bit. The way we're going to sum this is like this. We have all these blocks to add up, right? We have this formula for the volume. It's the function evaluated at some point in there times the, I'll go ahead and, did I use delta? Yeah, I did delta, okay. So delta x, delta y, right? So that's the volume of one of these blocks. So the way I'm going to add them up is this. I'm going to hold y constant, and I'm going to add up, see this block right here? That block right there? I'm going to take that block, and I'm going to add the next block here, and the next block here. And do you see, I'm just going to do this first row of blocks, this first row. Add them all up. So I'm holding my y constant. Remember, this is x. Y goes into the page. Z is out. So I'm going to hold my y constant, and I'm going to add up just along here, right? And then x. Does that make sense? Hold x constant and add up the y's. So what happens is you wind up having a double summation, not a sum of just one in one direction. You have to sum in both directions. So we're going to do a sum here, a double sum of this formula. Now, we're not getting into the nitty-gritty of this formula, right? We're just trying to get a general idea of where the idea of a double integral comes from, right? How many of these do we want? How many blocks do we want there? Infinite. So I need to take a limit, right? Let the number of them go to infinity, something like that, right? And so the double summation means that when we take this limit, we're going to have a double integral, okay? We're going to have a double integral. And then this right here is the height of the function at some point, right? That's the height of the function. And then this right here is your what? Dx dy, right? Dx dy. I'm going to go ahead and write it. Dx dy. Okay. Now, if I remove the dy and I remove the outer integral, you're back in Cal 2, aren't you? Okay. I mean, it's basically you're back in Cal 2. We've added this extra integration step that's going to happen. So we have what we refer to as like an inner integral and an outer integral. I'll get into more detail here, but I need to label some more stuff here. Let me get to this. Let me get to a point where I have some space right here. All right, so do y'all feel like y'all kind of understand where this is coming from visually? On the ground was that rectangle, right? And then we had that little patch here, that little patch that was delta x, delta y. Do you all agree that that little patch has an area to it, not a volume, right? What we normally do when we write this integral is we write double integral of the surface, or f of x, y, and we don't write dx, dy, we write d capital A. And what this means is with respect to area. With respect to area, because instead of looking at the dx and the dy on the ground, just look at it as like a little patch of area on the ground. Exactly. So we're saying we're taking the height of the height of the function times the area of the patch on the ground, and that should give us the volume of that little box. So this is our general notation. Okay, this right here is our general notation. But there's one thing I'm missing, and that is on a regular integral in Cal 2, don't you have to put limits of integration to get the area? A to B. For us, we have A to B and then C to D, right? In this notation right here, all I'm going to do is I'm going to call this whole thing on the ground, the whole thing, I'm going to call that R. You can either look at it as R for that rectangle on the ground or R for the region on the ground. What we're going to do is we're just going to put below the double integral R, like that. Let's see, let's just back up and see if this makes sense. What we're doing is we are taking some surface, right? The height of some surface, and we're multiplying it by this infinitesimal area on the ground, and that'll give us this box. And we're adding up an infinite number of them, right, over this entire region on the ground, this entire rectangle. And that should give us the total volume below this over that region. Now, if I restrict this, if I tell you A to B here, and I tell you here C to D, if I actually give you those restrictions, then we can write this like this. Or we can write it this way. You can write it either way, switching the order of these. But what happens is when you switch this order, it switches your limits of integration. So if I ignore this, we're doing it with respect to x on the inner integral. What's our limits of integration on x over there? A to B. So I put A to B here, and then here I put C to D. Now in this one, I'm doing it with respect to y first, right? So C to D goes here, and then A to B goes here. So these are three notations that all mean the exact same thing, all right? This is the very general notation. It's just saying, hey, I've got a surface, right? I'm trying to find the heights of that surface times the area, some little patch on the ground, over some region. This integral right here, the way you see it, does not require this region on the ground to be a rectangle. Let me say that again. This notation right here does not require this region on the ground to be a rectangle. It can be anything. We're starting with the rectangle because it's the thing that makes most sense to us, right? To have a rectangle on the ground? Okay. These are specific to, these two notations are specific to what we have here. Is a rectangle. Let's, I'm trying to think, do I want to do an example? That's this note right here. See, this is exactly the same thing I just wrote there. We're going to do an example now. Find, and this, is it obvious that this calculates the volume underneath the surface? I mean, that's what motivated the whole idea. So we have a problem here. We're supposed to find the volume, right? Find the volume under this surface on 0,2 cross 0,2. That notation is the first time I've used this in this class. Okay, so let me clarify what that notation means. When you see 0,2 cross 0,2, that is not cross product, okay? Because these aren't vectors. This is saying this is your restriction on your x's, this is your restriction on your y's. So think about it in two-dimensional space. If I were to tell you my x's were between 0 and 2, right? X's are between 0 and 2, but at the same time my y's are between 0 and 2, right? Then that would be any point that lives in here. Okay? That is the domain. This is the R. That's the region that I'm going to be, or rectangle in this case, that I'm going to be integrating over. There it is in three-dimensional space, right? So I basically want to take just these points that are in this region, plug them into that surface, and then when I do that, I'll get some surface up there. Let's go ahead and see it. Here's the surface. That's just the generic surface right there. Here is just the edge. Do you see the image of that rectangle up into the surface? And what we're trying to do is we're trying to find the volume. So we're trying to figure out what that volume of that chunk is. Let me take that surface out of here. There we go. We want that volume right there. Right? We look at it from the top, it looks like that box, but it's the surface, everything from that surface down to the XY plane. All right, well, you ready? Set it up. So what we're doing here is we're doing the double integral over the rectangle R of the function f of xy with respect to area. I'll say dA, right? That's the generic formula that will give us the volume. Now for us, I can change the f of xy to 16 minus x squared minus 2y squared, right? Okay, that's my f of xy. That's the surface. Now, I'm going to switch this to dx, dy, or dy dx. Do you think we'll get different answers? We shouldn't. We should get the same answer. Because it's a rectangle on the ground, it should not matter what order we went in. Remember those boxes we had? We go down one side first or the other side. Doesn't matter, all right? So here, why don't we do this? Let's go dy first, then dx, okay? And with that, I think I can now replace, let's replace my let's replace this r over here with what? Our limits of integration. Okay, so we start by looking at the inside one, dy. What were our limits on y? 0 to 2. Right, they're the same for x and y, but I want to make sure you understand. I'm looking right now for my limits on y, which were 0 to 2. And then the outer integral that I'm going to do is with respect to x, and that goes from 0 to 2 as well. So you can't really get this one wrong because they're the same. But you know, if y went from 0 to 3, then we want 0 to 3 on the inside one, right? All right, there it is. It's set up. Now, how do we do it? How do we do it, right? Like, how do you actually calculate this? It's not bad at all, okay? It's really, I'm not going to say easy. I hate it when I say things are easy and people are like, it's not easy. All right, but I think you will agree that it's not that bad. What we're going to do is rewrite it first, okay? That's the outer integral. Let me erase this. I'm going to give myself plenty of room here. Dx was my outer one, right? Okay. So that's this dx, and that's that outer integral, right? I'm taking everything basically in here. I'm putting this in brackets. All right, everyone. Time to find antiderivatives, right? You have three terms here, right? Okay. What's the antiderivative of 16 with respect to y? Treating y like your variable and treating x like a constant. So this is just like partial derivatives, but we're going backwards. So the antiderivative of 16 with respect to y would be 16y. Okay, now minus the antiderivative of x squared with respect to y. So you're treating x squared like a constant. What's the antiderivative of a constant? The constant times the variable, right? What's our variable? Y. So this would just be minus x squared y. And then one more. The antiderivative of negative 2y squared with respect to y. Negative 2/3 y cubed. Okay, do you all agree that that is the antiderivative of this with respect to y? Okay, now, fundamental theorem of calculus says that you take the antiderivative, then we normally would put that evaluation bar, right? Remember that? And then we put our two limits of integration, right? Which are 0 to 2. But this is where we need to say what is 0 to 2. What is 0 to 2 here? The y. So I'm going to put y equals 0 and y equals 2. So this outer integral, I'm completely ignoring it until I finish everything in here. I'm going to do everything in here first, get an answer, and then I'll do the outer integral. Right now I'm treating y like the variable, x like a constant, and I'm cranking away. So equals, I'm still going to bring this integral here. Okay, now the fundamental theorem of calculus, right? I actually plug in what first? 2 into that for y, and then I subtract from that what I get when I plug in 0 for y, right? Okay, I'm going to give myself plenty of room. I know I don't need this much room, but just again to illustrate, fundamental theorem, I'm plugging in 2 values, right? First, y equals 2 goes in here. Let's do that. 16 times 2 minus x squared times 2 minus 2/3 times 2 cubed. Right, that's what I get when I plug in 2 for y. Minus, and then this is real nice, isn't it? When you plug in y equals 0, boom, 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 kills them all off, we just get 0. Let's clean that up. Integral from 0 to 2, 32 minus 2x squared. Minus 16/3, right? Okay, that's what everything in the bracket turned out to be, right? But do you see I don't really need the bracket now? I am literally back in Cal 2 now, right? This is just an integral from 0 to 2 of this with respect to x. All you see in here are x's, right? X's in constants. Think you could do that? Yeah? Okay, let's go ahead and finish it up. Do y'all see there's 2 constants in there I could put together? That and that. So what is that? 96, 80/3, I think? Someone can check. 80/3 minus 2x squared dx. And now do your antiderivative. What is up with my voice today? Okay, antiderivative now.